So in the last video we looked at parsing, and in this video we're going to take a look at a parser generator called Bison. So if you go out there in Google and you look for things called parser generators, you can find several of them. Tools like Yak, which stands for Yet Another Compiler, which is pretty old. Bison is the next generation of Yak. It's been updated. It handles a lot more grammars and much more complex grammars, and now is very widely used on Linux and other environments. There's a tool called Ply, which is specifically for Python, that does the same thing as Elix and Yak in an integrated way, and there are others you can find for various programming languages. So don't think this is an exhaustive list. If you have another favorite language and you want to build a parser in that language, you might go look at a tool explicitly for that language. But let's take a look at how we can specify a grammar using the Bison tool. So just like Flex, Bison has an input file and takes an input file in a very specific format. So like Flex, at the top of the file you'll have something like this %open brace and %close brace, where you can provide various C definitions and declarations. After that, unlike Flex, we need to specify what the tokens in the grammar are. These are the terminals. And the reason we need to tell Bison these things is because it doesn't know what these are. Things that come from the scanner, and it has no idea how these tokens are made or what they consist of. It just knows it's a token. And so we have to explicitly say this using this %token keyword, followed by the names we want to give the tokens. And these names could be really any valid C identifier. I just used uppercase names because that's the convention. And these are going to come from Flex. So after we say these are our tokens, there'll be nothing else in this file that says anything more about them, because the grammar isn't concerned with what makes a token. On the next line, whoops, sorry about that. On the next line, I have this command %left, and this says that for the tokens plus and minus, we're going to assume that they should group to the left. In other words, their precedence is to the left. And since I'm putting them on the same line, that means they have equal precedence. And that's fine for plus and minus, because plus and minus should have equal precedence. Okay, and so this %token and %left define characteristics of the grammar. And then after this % symbol, and before the last one, inside there, we're going to specify all the rules of our grammar. And so I've specified a grammar for expressions. And this is similar to the grammar in the slides from last time. So I'm saying that an expression could be an expression plus an expression, or an expression minus an expression, or an expression inside parentheses, or a number, or minus followed by some expression. And you'll notice that the syntax is that I specify the name of the non-terminal on the left, and then I have this colon, and then I have each rule specified with a bar in between. And then when I want to end the non-terminal, I have a semicolon. And I could have lots of different non-terminals in one file. I just chose to put everything for this grammar within this one non-terminal, just to make sure that it fits on the slide. Okay, and if you pass this into Bison and you compile and run it, then it will match input patterns that match this grammar. Only there is one other thing we have to do. We have to define a scanner that will match all the tokens specified on the token line. So we also need to make a flex input file. And our flex input file would define what plus, minus, number, L_, and R_. And when we match a plus, then what the flex file is going to do, it's going to return plus, saying that we matched it. And when we match a minus, it's going to return minus, saying that it's been matched. And when it matches something that looks like a number, it's going to return number. And when it matches something that looks like an open paren, it's going to return L_. And when it matches something that looks like a closed paren, it's going to return an R_. And as the scanner processes the input file, it's communicating this information back to the parser, and the parser will then try to build the parse tree and prove that the grammar that was specified, in fact, can be used to describe an input file made up of these tokens. Okay, now one other thing you might question, since these actions in the flex file are nothing but C code, you may say, well, where is this plus coming from? Because this plus, for it to be legal C, has to be defined somewhere. Well, it is. It's defined in this include file that we placed here at the top of the file. We have #include calc.y.h, and this is a file that's going to be generated by Bison when it analyzes the Bison input file. And so it will make that file, and then we'll include it from our flex file. And each one of the names here, plus, minus, number, L_, and R_, they're actually from this token line in the parser file. Okay, so anything we say is a token, it's going to become a #define inside a header file, and then our flex file includes that header file and can then return that value back to the parser. Okay, and that links these two things together. Now, if you're thinking, wow, this can't be enough to make all this work, well, that's a fair feeling, and there's a lot of code happening behind the scenes that we don't need to worry about, because Flex and Bison are going to work together in order to see to it that they can parse the file in the right way using this set of tokens and the grammar that we defined on the previous slide. Okay, now what you often want to do when you write a grammar is you want to specify some actions to take as rules of the grammar are matched. Right, that's what we're doing in our flex file. Whenever we see a token, we can then execute some C code. Well, we can do the same thing in a Bison file. We can specify an arbitrary action in C code for each rule in the grammar. So what we might have is, for example, when an expression matches the rule expression plus expression, we could put some C code right beside it inside braces that describe what to do when this rule of the grammar is matched. Right, and here I just put a comment, but for this other rule where we match minus expression, we might print unary minus. Okay, we can put any code inside these braces we want to. If you can imagine C code to put there, if you can imagine the C code you want, you can put it there. You just have to implement it. Now, just putting in printfs would get boring really quick, and there's only so much you can do with printfs. So what we really want are much more advanced actions that exploit deep knowledge about what the grammar means at any particular rule. And one thing that Bison does to help in this process is it allows you to associate a type of data with each token and non-terminal. Now the first thing we have to do inside the Bison file is declare a union. And inside this union, we place all the fields that we need to have inside this union. A union is a lot like a struct. The only difference is that within a union, you can only ever access one of the fields at a time. You can't access multiple of the fields the way you can in a struct. Then, after you've placed all the fields you want inside this union, you associate the fields of the union with specific tokens and non-terminals using the type keyword. And this goes inside your Bison file. So after you've defined your tokens, you would then say %type val inside these brackets. You'd say associate type val with the non-terminal expression and the terminal number. And that basically is a way of saying that anytime the grammar matches a rule that's an expression or a rule that's a number, there is an integer value associated with it in memory. Right, so now anytime we see a number or an expression, anywhere in a rule, it's automatically associated with an int value. So this number is really an int value. This expression is really an int value. This expression is really an int value. And the result of the expression that it's creating is now an integer value. And you can actually imagine that in memory somewhere there is an integer value associated with each node in the parse tree as it's figuring out what that parse tree looks like. And not only that, we can use them for computation. Now, in order to use it for computation, we have to refer to the int for each part of the rule separately. So the rules are the output of a rule is always $$. So that's ultimately what the rule is creating. And the first position within a rule is $1. And so number would be $1 and expression would be $1 because they express different options for the rule. You can't match both number and expression plus expression at the same time. So you would either match number, and number would be referred to as 1, or you would match expression plus expression, and they would be referred to as 1, 2, and 3. So $1 would refer to the first expression, $3 would refer to the second expression that you're adding, and then those two things get added together. Or we're saying you're going to add them together, and then they would produce the resulting expression $. Okay, so some things to note. $$ always refers to the output of the rule. $n refers to the nth position within the rule, like 1, 2, or 3. And the count starts over with each alternative in a rule. So number starts with 1, and expression plus expression starts over and counts from 1 to 2 to 3. Okay, now this leads to a very intuitive and beautiful syntax. Okay, so the action for a rule, if we actually wanted to compute the result of the expression, would be something like this. When expression matches a number, we would say that the output of the rule is simply equal to the number, $1. When it matches expression plus expression, we would say that the output of the rule is simply equal to the first expression plus the third expression, right? $$ equals $1 plus $3. And that's really intuitive and makes a lot of sense. Okay, now here's the resulting Bison and Yak file, where we associate actions with all the rules. Now you see that I've added the type, val, expression, number here. I've added the union to the top of the file, and note this % does have to go there because we are telling Bison that this is a special union. It's a union that describes the kinds of terminals and non-terminals it's dealing with. So this is the special construct Bison understands. Okay, and then associated with each rule, we specify the action we want to take. So when we match a plus, then the result is 1 plus 3. When it's minus, the result is 1 minus 3, right? When you have an expression inside parentheses, then the output is simply equal to, the expression in the middle, which would be $2. When you have a number, the output of the expression is just the number. And when you have minus followed by an expression, the output is just the negation of the expression, right? So these rules actually explain how to compute the result of an expression at each step of the parse tree, where this grammar rule is applied. One confusing thing sometimes about interpreting these actions and understanding the order of their execution. One confusing thing about actions is understanding the order of their execution. And the basic rule of thumb that can help you think about it is that actions always execute from the leaves of a parse tree up to the root of a parse tree, right? Because we're always trying to match terminals first and then build those terminals into some, larger non-terminal structure and then slowly grouping non-terminals together to make other non-terminals until finally at the top of the parse tree we have our full expression. And so, these rules execute from the bottom up, from the bottom of the parse tree up to the top of the parse tree. So when you're thinking about how actions in these rules work, you should draw a parse tree and imagine the actions executing as you move up the tree. Okay, now we've added actions to our Bison file. We need to go back and take a look at our Flex file again. There's something else that needs to happen here. Namely, when we match a number, we can't just return number. We actually need to say what the number is so that when we're computing the result of the expressions, we're actually using the actual number. And so what we're going to do is add a little bit of extra code to this rule. And it looks a little bit complicated at first. Whoops, sorry about that. It looks a little complicated at first, but there's a lot of logic here that you can start exploiting on your own, writing your own rules. So YYText is a special pointer provided by Flex that points into an array at the first character that matches this token. So wherever this rule 0 to 9 plus matches within the input file, YYText points to the first character in a character array for its very first character. And what that means is that YYText is essentially pointing to a string that represents that token. So we can pass that string to A2I, which is a library call in math.h, to convert the string into an integer. Okay, so that explains what this function is doing here. We're actually turning the string that we matched using that rule into an integer. But then we're going to save this integer in a special location so that the parser now can associate an integer with a number. And you know we declared that union before that had val inside of it? Well, there's a special global variable called YYLVal, YYL left value, right? Where we're allowed to save, I apologize, where we're allowed to save the values of tokens that we find, right? So each time we match one token, we can set the corresponding field inside this global YYLVal to have the correct value. And since we associated number with the val field, then we're going to set val to have the number that we read from the input. Okay, and after we do this, then we're all set. When we read in these tokens, if we match plus, minus, L paren, or R paren, there's nothing else we need to do. If we match number, then we convert the number into an actual integer, and then we return saying we match a number, and then the parser is going to take care of everything else. Now Bison expects number to be an int, but number is really just a token passed from the scanner, and that's why we have to extend the action associated with number to actually compute the int value. Right? This is critical. This is what ties everything going on in the parser together with what's going on inside the scanner. So really look at this example and make sure you understand what's going on here and why we have to do this. Okay, if you want to try this out and work this example on your own, it's already on GitHub. So I'll log on to VCL. If you haven't already checked out the projects directory, check it out. Change into lecture code/parser, and then execute these commands. So I'm going to change into lecture code, parser. Inside of here is a makefile, and if you look at the makefile, for the all command, you'll see that it calls Bison and it calls flex, and then calls GCC. This is the sequence of commands you need to convert the calc.y file into calc.y.c and calc.y.h. Right? We need calc.y.h because that's used by flex. And then the flex command converts the calc.lex file into calc.lex.c. And then using GCC, we compile all these things together. We link with the flex library, build a binary. And so rather than execute these commands one at a time, I'm just going to type make all. It's going to build it all for me. And then I can run the calc binary and see what it does. And if I write 1 plus 2 plus 3, it tells me the result is 6, which is correct. And if I write 1 minus 4, it tells me it's minus 3. And if I write 1 minus 2 plus 1, it tells me the result is minus 2, which is correct. And if I write 1 times 7, it tells me there's a syntax error. And that's because the scanner realizes that star is not a valid token in my scanner. And so, of course, that's not something that I'm allowed to enter. Okay, so look back at these two input files, try to modify them, try to make this parser do something else or do something different, and see if you can figure out how to modify it in the right way, like, for example, to support new operators, or exploit other kinds of values, like floating point values. And that'll really help you evaluate what you understand and what you don't understand. Okay, thanks guys.